because I'm going to start the introduction. It will be a couple of minutes just to, as people are still coming in. So thank you once again, everybody. Lots of participants are still trickling in, and really thank everybody to participate in this effort that we started now 2 weeks ago. This is a joint effort between the Spin Phenomena and the Disciplinary Center SPICE and the Collaborative Center SPIN+X between Kaiserslautern and Mainz. And I'd like to thank my organizers, co-organizers, Karen Evershore, Cite, co-organizer of SPICE, and the speakers from SPIN+X, Martin Schliemann, Burkhard Hillebrands, and Matthias Klaue. And these talks, as you see, they're going to be on Zoom regularly every Wednesday at 3 p.m. And live stream on YouTube channel, and please disseminate it as much as possible. We would love to have lots and lots of people participating during this time, and we will probably continue forward after this. The talks are available, should be available immediately, a few hours afterwards, because it takes a little processing in the SPICE YouTube channel. So anytime you want to review anything, you will be there. And also linked, of course, if you go to the SPICE website, directly looking for the speaker and the schedule, you should see it there. The Zoom webinar format means that when you come in here, you're as an attendee, that you can hear me and hear us and hear the talk, but you will not be able to directly talk, but you can use the question and answer format to send questions that I will be monitoring together with Karen Evershore Cite during this time, and we will try to answer some of them if they are just technical things, or try not to interrupt the speaker, in this case Carlo, during this period, just so to continue the flow of the talk, unless it is something that requires some discussion. I would like to remind that there's also other important online seminars, particularly in our field of spintronics, topological physics. One that I kind of would like to give a heads up is online spintronics seminar that also gives talks on Tuesdays and Fridays. So you could essentially see a talk every day. And I thank you very much for participating in this one. We have also, we have, as you say, already next week, Tobias Kampfer will talk about ultra-fast spintronics, and followed by Pietro Garbandella and many others coming up. And you can see the list again on SPICE. I would like to now introduce and thank Carlo Beenakker for giving the second talk in here. Carlo has been a professor in Leiden since 1991. And is very well known in the world around his work for mesoscopic physics, quantum Hall effects. He was given several awards like the Royal Cell Prize for quantum Hall effect and quantum effects in electronic and mesoscopic systems. He's a member of the Royal Holland Society of Sciences and the Royal Netherlands Academy of Arts and Sciences, now for close to 2 decades, and received the Synopsa Prize as well in 1999. And then recently also obtained an ERC Advance grant in 2019 on related work that he's going to talk about today. And then the latest times, he's been one of the pioneer theorists looking at the Majorana physics, particularly many of it that has appeared from Holland and the Netherlands. I also, like to say a couple of things that are interesting. So he comes from 3 generations of physicists. As you can see clockwise, you see a very young generation with very dark hair from Carlo there on the left, and several family members around. And he also started in technology very early on in 1988. He sent his first email to Beenakker. So he is also very well connected, even in the communication age, to mesoscopic physics directly. As you can see here, this is just Beenakker as the email address that he had to use at the time. So with this, I am going to stop sharing, and I'm going to ask Carlo to please share your screen, and I'll mute myself. And you can start whenever you like. Thank you very much.
Yes, spotlights.
Okay.
And it works, right? you guys can hear me and you can see me. So I'm very happy to be here. I'm actually not there, but I see lots of friends in this impressive list of participants. Many friends. I wish I could say hello to you, but that's not possible. So the best I can do is try and offer you something which you may find interesting so that you'll stay with us for a little bit longer. It won't be too long, don't worry about that. So this is actually a topic, it's a topic of my ERC grant, which I was very happy and honored to receive last year. And it's what I plan to do in the next couple of years. It's a new way of looking at Majorana physics instead of doing the vortices or these things at the endpoints of Josephson junctions or endpoints of nanowires, which has been pretty much beaten to death, at least theoretically. I would like to do a different way, which is edge modes, edge vortices, but then do the usual stuff, which is braiding, fusion, the whole works. And so this talk today will be a bit of a mix between a colloquium talk where I won't assume much background, basically giving you an introduction to this recent field, which I think is really promising. But then also there will be some of you who are actually experts. And so I want to have something new to offer to you as well. And that will be a preprint which we put out on the archive just last week. So this is really, really recent stuff. It's about fractional charge transfer and the noise associated with fractional charge transfer. The paradox actually with that. So this is a teamwork, and many of my team members are listening in, and hello to you all. So this is Fabian and Aurélien and Michał and Dima and Omri and Inanch. It's a team effort because it's a project which you've been working on for quite some time, even though it was finished only very recently. Okay, so without further ado, let me go back in time. 1999 was the birth of Majoranas in superconductors. So of course, Ettore Majorana lived in the 1920s, and probably in other branches of physics, the whole notion of a Majorana fermion was not completely forgotten or unknown. But in condensed matter, and in particular in superconductivity, this happened in the summer, remarkably enough, within just 2 weeks of each other, 2 papers on the archive in the summer of 1999, who noticed that actually quasi-particles in superconductors could be understood as Majorana fermions, and that you could do amazing stuff with them. There's the Majorana metal, that's Sentin and Fisher, and there is the Majorana vortices and the edges and the fractional and the thermal quantum Hall effect. I'll show you that in a moment, by Reed and Green. So this all started, yes, more than 20 years ago. And still today, experimentally, it's not quite resolved. It's very much an open problem experimentally, but theoretically, we've come a long way. And some of these developments I will be happy to present to you in the next 45 minutes. So let me show you the basic experiment, which is basically what Reed and Green proposed. So this is the analog of the quantum Hall effect in a superconductor. Now, superconductors typically do not have edge modes. You know, quantum Hall effect is all about edge modes. Superconductors typically do not have edge modes, but they can have edge modes. And they have to be two-dimensional for that. And superconductors with edge modes are called topological superconductors. Now, you typically need some exotic form of pairing. This is actually one of the big experimental challenges to realize a topological superconductor. But if we assume that these superconductors exist, and then you could say, well, can we have a quantum Hall effect in a superconductor? Now, of course, a superconductor is a short for electrical current, right? So it doesn't make sense to talk about its resistance. Its resistance is 0. But they're insulators for heat. So the superconducting analog of the quantum Hall effect is a quantization, not of the electrical conductance, but a quantization of the heat conductance. That's what's called the thermal quantum Hall effect. And I guess you all, if I would be looking at you, I would now ask you, please tell me the quantum of electrical conductance. And some of you would raise their hands and they would say E squared over H. So I would know that you're still with me, but I cannot see any one of you, just so you know. I'm just looking at myself, actually, which is kind of crazy. So I cannot ask this question, But I presume many
half of them
know,
say yes.
Yes, many of you know E squared over H. And so you might ask, and this would actually be a trick question, what is the thermal analog of E squared over H? It's a miserable combination of fundamental constants. Here it is. There's pi squared, there's k squared, there's t, there's h. And then actually there is a 6. And it's all about this 6 because the actual quantum of thermal conductance has a 3 there. The quantum of thermal conductance has been measured. There are many experiments which measure the quantum of thermal conductance, typically using phonons. And it should have a 3 here. But if you have these edge modes of a topological superconductor, the quantum is a 6. And this is, okay, it's not very dramatic, of course, 3 and 6, just a number, but it has a really dramatic message because it tells you that actually a Majorana fermion is only half an electron. It's half a usual fermion. And just to bring home to you how remarkable this is, I guess you all are familiar with the fractional quantum Hall effect. That fractional quantum Hall effect where the conductance quantum is not E squared over H, but E squared over 3H or E squared over 5H. Now, all these fractionally charged quasiparticles, they all have the same unit of thermal conductance with the 3. So there's no fractionalization of thermal conductance for any anion. That's a really crucial thing to keep in mind. Anions are non-trivial because of their fractional charge, but they carry heat in a trivial way, just like an electron, just like a photon. In fact, fermions, bosons, anions, they all carry heat in the same way with the same quantum, which has a 3. And the only exception we know is a Majorana fermion. A Majorana fermion has not a 3, it has a 6. So it's really unique. And to measure this is an amazing breakthrough. And this has happened. This has happened not so long ago. This was 2018, a team from the Weizmann who measured the half-integer thermal quantum Hall effect, where you should take into account half-integer means the unit is 1/6 instead of 1/3. And they measured this, and there's an extra factor of 5 there because somehow they were not in the lowest Landau level, but that's somehow a detail. So they measured this thermal conductance, which was 5/2 instead of just 3 or 4 or 5, 5/2. And here's the experiment. So you see this, here's 2.5. Now this experiment, you know, as all experiments, it's a first, it's amazing, but there are questions. So here somehow seems to level off at 2.5, but then as you lower the temperature, it seems to go up, which is kind of crazy, right? You would expect it to, lower temperature should be better, right? So you would expect it to level off at low temperatures. Instead, it goes up at low temperatures. This is again a topic of intense research and interest, and it's beautiful, but it's not a superconductor. It's not a superconductor. In fact, it goes back to this very first paper of Reed and Green. They weren't interested in superconductivity at all. They were interested in the fractional quantum Hall effect because they discovered, Moore and Reed and Green discovered that the 5/2 state of the fractional quantum Hall effect behaves like a topological superconductor. And so this experiment basically shows that what Reed and Green predicted in 2000, 2 decades later, actually works. But my interest is in you know, topological quantum computing, qubits, and you really want superconductors for that. So this is a beautiful experiment. It shows that the physics makes sense, but I want to do this in a superconductor. And so you could ask, what is the superconducting realization of this? Now, this also is a really interesting history. It has a name. If you won't believe me, just Google it at this moment. Google angel particle, and you'll get thousands of hits. We all know the God particle, right? The God particle is the Higgs boson, and the angel particle is the Majorana fermion. So this was a beautiful discovery from 2017. Angel particle discovered, matter and antimatter, you know, all kinds of the usual buzz and hype which you have when you make a big discovery. And it did not end well. It did not end well, and we could have known about this because when you think angels, you think about the movie Angels and Demons. And yes, there was a demon actually which killed the angel, and it died. And this was basically a group from Würzburg, Lawrence Molenkamp and his friends, who found that the experiment did not deliver. This particular platform did not deliver. It was a false alarm, as it happens quite often, of course, in physics. There's nothing to be worried about this. False alarms are there, and you just have to work harder. But this was a bit depressing. And there's some good news now. There's a recent paper published this year, which is new evidence that indeed these Majorana modes, these chiral edge modes, do exist in a different platform. And you know, this will, of course, be validated, and there will be more experiments. But this is definitely one line of research which is really promising. There's a whole bunch of platforms, and I'm pretty sure we will have reliable topological superconductor with edge modes and basically repeat all the quantum Hall physics in a superconductor. So the experiments are difficult, but they're not hopeless. There's lots of activity, and I can just stand by the sideline and applaud these people. So I won't tell you much more about this. I will, you know, move forward and say, okay, suppose we have these things, what can we do with them? And the Holy Grail here, really the Nobel Prize winning experiment. I mean, this is, there's no argument here. The first person to demonstrate braiding of Majorana fermions wins the Nobel Prize. With Nick Reed, of course, don't know about, with Nick Reed and perhaps Moore and Green, I don't know, but the experiment it will be an absolute breakthrough. This is something which was predicted in this paper here, that if you take two Majorana fermions confined to a vortex, that was the realization they had in mind. So a vortex is like a hole in a superconductor. And so even though the superconductor is gapped, when you have a vortex, you make a hole and you can trap a Majorana fermion. The Majorana fermion is trapped and bound to the vortex. If you take two vortices, now comes the theorist speaking, of course, you take two vortices, move one around the other, then you execute a unitary transformation. And that's the unique thing. We're all familiar that exchanging particles executes a phase factor +1 for bosons, phase factor -1 for fermions, any phase factor for anyons, Frank Wilczek, any phase factor for anyons. But phase factors are what we call abelian operations. You know, you multiply one phase factor, you multiply another phase factor, you can exchange the order, it doesn't make a difference. You cannot build a quantum computation by multiplying phase factors. It's too trivial, right? It's just, you can multiply as many phase factors you want. In the end, you just want to know the total phase increment. To build a quantum computation, you need to multiply unitary operators, unitary matrices. It could be simple matrices, 2x2 matrices, that's okay. You can build any unitary out of 2x2 matrices, but you need matrices. Matrices do not commute. It's called non-abelian operations. And non-abelian operations allow you to do quantum computations. And so the unique idea of Kitaev, who realized how you would be able to apply this, the idea was that if you would had a batch of Majorana fermions bound to vortices, you would move the vortices around and in this way carry out computation, build a quantum computer. And this would be a very robust way of doing it because it's like making knots. You either braid them, that's what it's called, or you don't braid them, so there's no ambiguity there. And so the buzzword here is topological quantum computation. And there are companies, betting that this will be the platform that will deliver. Microsoft is one of them. There's a big lab not far from here in Delft, and there's a lab in Copenhagen, and there's a research team in Santa Barbara, hoping that actually this will be the way in which the quantum computer of the future will work. But of course, for that, we first, A, need to have these Majorana fermions, and B, we need to be able to move one around the other. And of course, this is the theorist's invention that you think you have this vortex, pick up the vortex, move one around the other. It's not going to work in that way. We can be really very sure about that. And so this is a problem. How do you move these things? Vortices are basically classical objects, they're massive objects. You cannot just move them around. And so now comes Shucheng Zhang's idea. Shucheng Zhang had an idea, which he published in Proceedings of the National Academy of Sciences in 2018. We have these edge modes. These things move by themselves. They just propagate. All we have to do is make some intersections, make sure that these edge modes do this or do that. They will braid by themselves. Now, perhaps making a quantum computer would be a bit tricky, but certainly you could demonstrate braiding, win the Nobel Prize, and retire. That was the idea. And that triggered me and a whole bunch of people. And this is basically the prehistory. Now comes the history. And we published this in 3 papers. this idea. And here I should give credit and make a deep bow. I'm going to do that now, deep bow, for one of the participants who's present here, and that's Anton Akhmerov. So people had thought about using edge modes with Majoranas for many papers, but this was always these excitations would appear spontaneously by quantum tunneling. It was a very undeterministic way to do stuff. You know, if I tell you take two vortices, move one around the other, you're not going to wait for some quantum fluctuation to make this happen, right? You just want to pick them up, move one around the other, and that's it. So tunneling, interference, quantum fluctuations, it's all bogus if you want to do a quantum computation. Quantum computation has to be on demand. The fermion has to, the qubit has to be there. You have to do this operation on the qubit. And I was, yeah, this is, I can tell you, right? I mean, even though it's recorded, it's no secret. I was looking for a good topic for an ERC grant proposal, and I needed one idea to build an entire research line, a 5-year research line. Now, I'm sure many of you have been through this process, and this is the hardest thing to do. It's, I mean, of course you have to write this research proposal, it's 50 pages, but that's just work. You just, every morning you devote a couple of hours and that's good. But you need this one idea which will basically unify 5 years of work. This is not my strength. I work from one project to the other, right? 1 month to the next month. So I needed one idea for 5 years of work. I went to Delft. I still remember very well. You probably also remember Anton. I took the train to Delft. I went to you and said, please, Anton, give me this idea. And Anton, generously as he is, gave me the idea. He scribbled it on really a napkin. It was just 2 lines of text. And this idea has turned out to be incredibly fruitful. This is a way to create Majorana zero modes, how we call them, on demand, braid them on demand. And this is basically what I hope to be doing now, and what I'm doing now, and I hope to be doing in the next couple of years. So let me first have a couple of pointers which you need to know. First of all, when you think about edge modes, you say, okay, let's just apply a voltage source and inject particles, right? These will be Majorana fermions, and we're done. What's the difficulty here? We do that all the time. There's a big industry which is called it's quantum optics for electrons, where you create single electron sources. So just create a single Majorana fermion, inject it into this edge mode, and you're done. This was Zhang's idea. It does not work. It fails for a dramatic reason. The reason why it fails is because Majorana fermions are fermions. They're fermions. They have fermionic statistic, abelian statistics. They're not anyons. So to inject the Majorana fermion in an edge mode, it's good. You can write lots of papers on it. It's interesting. They have this fractional thermal quantum Hall effect, but you cannot use it for braiding. They're abelian. They're abelian particles. The same, actually, we should have known this, right? Because, for example, people are hoping that perhaps the neutrino would be a Majorana fermion. There's this big research going on, right, for the neutrino to be a Majorana fermion. Do you think the neutrino would be a non-abelian particle? Of course not. It's just a fermion, right? It's just like an electron. So this is a big confusion going back to the origins of the field, that we somehow attach this notion of a non-abelian anion to a Majorana fermion. It's a mistake. A Majorana fermion is a fermion, it's abelian. You cannot build a quantum computer out of it, period. So what you need to do is you need to inject vortices. Now, vortices are great. Vortices are non-abelian, but the Majorana fermion is abelian. So what we need to do is to have a source of vortices which will inject single vortices into an edge mode. And this is the problem the suggestion which Anton gave me back in 2018. He said, I know how to inject a vortex into an edge mode, deterministically on demand. And that's a Josephson junction. The most elementary thing there, a Josephson junction does what a voltage source would do for fermions. Why does a Josephson junction do that? For a very basic reason. If you have a Josephson junction, you can easily make a what's called a 2-pi phase slip. No, a Josephson junction has 2 superconductors, they have a phase difference, and you can make a 2-pi phase difference, which basically brings the system back to its original starting point. It's called a quantum phase slip. It can happen randomly, But it can happen on demand. You can make a voltage pulse. You can make what's called a flux bias. It's really routine to make 2-pi phase slips. But now comes the magic. A 2-pi, when we say 2-pi phase slip for a Josephson junction, we're talking about superconducting phase. So that's for pairs of electrons. So if there's a 2-pi phase shift for pairs of electrons, there's only a pi phase shift on the edge. There's only a pi phase shift for fermions. So on the edge, you will have made a domain wall, a pi phase domain wall. This pi phase domain wall will travel along the edge, as any excitation would do. It's a topological excitation, if you wish. It's a vortex. It's a vortex. The phase winds. It's a pi phase domain wall. It's a vortex. And this has non-abelian statistics. That's the idea. And all the rest just follows from that. Then you can think about how to do braiding by having intersections. You will have to worry how to detect these edge vortices. It turns out that they're charged. Not by themselves. They themselves are charge neutral. But if you have two edge vortices, you can fuse them and their charge will be E over 2. Not E, but E over 2. Remember, Majorana fermion, half an electron. The charge of two edge vortices together is plus or minus E over 2. And you can also detect braiding because braiding will flip the sign of the charge. If you braid two vortices, their sign will flip from plus E over 2 to minus E over 2. So all the building blocks are in place and we can proceed. So this, well, I have a couple of slides basically to illustrate that. So this will be the device, Josephson junction, flux bias, increment the superconducting phase by 2 pi, inject edge vortices. You'll notice that they propagate in the same direction here. That's a bit unusual. I mean, typically in the quantum Hall effect, you would like to have stuff propagating in opposite direction. Here, you really want them to be propagating in the same direction. But that you can do. There's this magnet. I mean, this is all topological insulator phenomenology, stuff which we understand very well. To have co-propagating edge modes, edge vortex here, edge vortex here. Here they fuse. They become a conventional Dirac mode, which is the conventional fermion, and it will have a charge of plus or minus E over 2. So you can detect it. This is I said domain wall, right? So here's this domain wall of the phase. In fact, we have a complete theory for this. It's not just a delta, it's not a step function domain wall. It has a certain width. It rises with a certain width. The width, I call it the injection time of the edge vortex. And the width is given. Do I have a formula for that? No, there's no formula for that. The injection time, this the width, it's psi 0 over W times d phi dt, times 1 over d phi dt. So this thing here is very narrow. This thing here is very narrow if the junction is wide compared to the coherence length. And that's what you want to be in that regime. You want to be in a regime that this is almost a step function. And it will be almost a step function if the length of the junction, so the separation of the two edges, will be long compared to the coherence length, which is kind of easy to do. So then you will have almost a step function increase. And the spacing of the vortices can be very large. So you have really well separated, well identified edge vortices. What is the charge on what is the current carried by an edge vortex? There's a beautiful formula by Piet Brouwer. Are you listening, Piet Brouwer? He might be there, right? If he's there, I greet you. There's a beautiful formula which says the current is just a derivative of the phase profile. So if we have a phase profile which increases by pi, a pi phase domain wall, if we have a phase profile which increases by pi, it means that it carries a current. Well, you integrate this from beginning to end, which means you have the final phase minus the initial phase, which is pi. You divide by 2 pi, and you get E over 2. It's that simple and that beautiful. And so here is, again, another plot. Here I use a voltage pulse instead of a flux bias to inject them. You can do either. And in fact, here I have two junctions. So I'll be injecting a pair of vortices here, and I'll be injecting a pair of vortices here. So there will be 2 pairs of vortices. Here they are, 2 pulses, separated by some time, which is basically the travel time, but the pulses are narrow. They have opposite charge. This will have a charge of plus E/2, then this will have a charge of minus E/2, all given by this formula here. And if you braid these vortices, their charge will flip. Here's another plot for that. So here this is the usual way we describe braiding. We make a world line. We use world lines where we say these particles go together and then they intersect. And so here there are two, you see I'm creating a pair of vortices here and I'm creating a pair of vortices here. So I have two pairs of vortices. Here they are. Two vortices here in red, two more vortices here in blue. And if their world lines braids, you see, here I have an injection time T1. If T1 is 0, it means that I inject everything at the same time and then they don't intersect. There's no braiding. But if I delay it, then they intersect and you see the current, the sign of the current changes. So all of these are somehow microscopic calculations. You see, we have a whole curve. We have all kinds of wiggles here. So we have some sort of a complete theory for this. It's not just a hand-waving argument. There's a real theory for this. And somehow it works, and this is how you would detect the braiding, and it works, at least theoretically it works. So this says primer 4, because I'm basically done with the colloquium style introduction, which is good. I've been speaking for half an hour. I have 15 minutes now to go to the more specialized seminar, which I think don't go away. I think it will still be interesting. So I go back to this thing here. This says charges E/2. Now, this is an expectation value. So this charge of E/2 is on average. And you might say, okay, that makes a lot of sense. Probably what you're telling me is that sometimes you inject charge E, sometimes you inject charge 0. And so at the end, you're always injecting 0 or E. It's just that the average is E/2. It doesn't seem possible to inject E/2, right? It doesn't make sense. And that's the question. That's the question we answered in this preprint, which we posted last week. And this goes back to a paper, important and seminal paper by Schrieffer and Kivelsen, 1982. This was a paper written after the first fractional charge was discovered. This is the Schrieffer-Heger model, Yakif and Rebbe, solitons, polyacetylene chains. You've probably, I mean, it's text course material that there are these, we would now call them topological insulators, which have localized charge, which is a fraction of an electron charge. So these are charges in a gap. These are gapped systems, but they bind somewhere a defect with charge E/2. And when this was discovered in the 1980 or 1980, I think, the same question was asked: oh, is this really E/2, or is this just charge hopping on and off this defect so that it only seems that it's E/2, but sometimes it's 0, sometimes it's E? And this was answered by Kivelsen and Schrieffer. The title says it all. No, this is a fractional charge. It's not charge hopping on and off. It's really fractional charge. It's a fractional charge of E/2. Now, this is a gapped system. We have a gapless system. Does it work in the same way? Am I really able to inject charge E/2 into a normal metal? It doesn't seem possible, right? And I noticed Wolfgang Belzig is among the audience, at least he was among the audience when I started talking, who's, let's say, the expert in counting statistics. And there is this basic dogma of counting statistics that everything should be discrete. The cumulant generating function should be 2-pi periodic, meaning you can only inject integer charges. Only integer charge can enter a normal metal. So if you have half integer charge, on average, you would assume that the noise has to be at least E²/4. E²/4 is the noise of a binomial process. So it's what happens if you sometimes inject charge 0, sometimes you inject charge E, each with probability 1/2, then the noise, the variance is E²/4. Now comes the paradox. When we worked on this 1.5 years ago, we had a theory for calculating these things. And the theory is called Bozonization. And Bozonization is a well-known technique in this field. It's also a technique for theorists. It's a technique for experts. It's easy to make errors. And this technique said the charge is completely noiseless. The variance is 0. It's not E/4. In fact, all cumulants are 0. All cumulants are identically 0. We had this result probably a year and a half ago, and we buried it. We buried it because it says this makes no sense. We're not going to write a paper where we use some sophisticated technique called Bozonization, and we says it tells us we're injecting charge E/2 without any noise. So we buried it, and this explains the long author list of this paper, because in the year and a half since we buried it, whenever a new student or a new postdoc would arrive, I would give this problem to them and say, resolve it. And we had an enormous amount of dead ends, because that's how progress, I mean, I could even now perhaps digress a little bit, because I actually have slides on Bozonization, but I'm going to skip these slides because I was taught that I should speak for 45 minutes. And if I'm going to give you a primer in Bozonization, that's too long. So I'm going to skip it. You can ask me about them later. And first I'm going to show them here so that the experts can look at them. And I want to tell you a bit of something, a philosophy which you may or may not share, which is the following. Many modern papers, and I see this as a new trend which is pervading also our community of condensed matter theory. I hate it. It's at the end of the paper, it says author contributions. I'm very much against it. I think it goes against the spirit of research projects. Research project, the way I experience them, is like this. There is a problem. A whole bunch of people work on them. There are 10 things which don't work. And then finally, there's one thing which works. What do? Are you going to write an author contribution? Author number 1, 2, 3, 4, 5, 6 worked on this but couldn't solve it. Then came author 7 and he solved it. Are you going to write that? It makes no sense, right? Author contributions makes no sense in a field, in a research field like physics, where it's not a linear progression. It's not you did this, you did the computer simulations, you wrote the paper, you analyzed the data, you wrote the manuscript, you made the figures. It doesn't work that way, at least not in my group. So we had a whole bunch of dead ends, things which did not work. This is the other Bozonization slide. The experts will have seen everything. So here is the cumulant generating function. Bozonization tells me the cumulant generating function is linear in psi. A cumulant generating function with a linear in psi means all cumulants vanish except the average. There's one extra term, mercifully, equilibrium fluctuations. But we're at 0 temperature. What do you mean equilibrium fluctuations? No, that's not quite how it is. So now comes the resolution of the noise paradox. So this is a plot. It's a bit of a busy plot. Let me walk you through it. So this shows one of these pulses, right? It shows one of these pulses. I just zoom in on one of these pulses. Shh. Please, more quickly. Yeah, here's the pulse. I zoom in on one of these pulses. This is the average current. I want to detect this pulse. How will you detect this pulse? You have this thing that's called the detection window. Detection window is some function. You start detecting, you start counting electrons. You count with unit efficiency when you think something will happen. So this counting window, this blue thing, has to be 1 when you think the pulse will arrive. And then after a while, you're fed up and you shut it down. It's always like that, right? I mean, you start, you count, you shut it down. And you can make this blue thing wide if you want to be sure to capture the whole peak, but that's how it works. And this blue window, this counting window, multiplies. So the average current is the derivative of the phase multiplied by this detection window. But since the detection window is 1, where the thing says peak, average Q is E/2. But now comes noise. So we're at 0 temperature. There's no KT. There's no thermal noise. I tell you this thing here is noiseless, gives you no noise. But what about the noise from this WT? Yes, there is a noise from WT, and this is basically a formula which goes back to these guys, Levitov, Lee, Lezovic, 1996. It's not quite there in this form, but you can extract it from their paper. So the noise associated with this counting function, you have to Fourier transform the counting function, gives you W of E, absolute value squared, multiplied by E, integrate from 0 to infinity. And for example, I did this just, with Mathematica for this blue curve. For the blue curve, I find a noise which is 0.17 E squared. If instead I take a Laurentian, still peaked at 1, I get 0.06 E squared. I can actually make it smaller. I can make it as small as I want. And this resolves the issue. So it's not completely noiseless. We're not saying that I'm injecting E/2 charge with zero noise. That would be impossible. But I'm injecting E/2 charge with a noise which is much smaller than E squared over 4. E squared over 4 was the naive binomial estimate. It's much smaller. Here it's 0.06, here it's 0.17. So indeed, I can be almost noiseless, but because it's almost noiseless, there's no paradox. So that's how it works. That's the resolution. And this makes me very happy. So my clock says 43 minutes. I have 2 minutes to wrap up, which I'm going to do now. And then you guys were not, I hate this actually, that you guys were not able to ask questions during the talk. My usual mode of giving lectures is that you ask questions, I talk about it, I look at you, I get feedback. And now this seems like some crazy performance just looking at myself. But okay, that's how it is. Yes, edge vortices. I'm in love with edge vortices, not just because I got this grant, but because I think it's absolutely amazing. It's a beautiful topic. It's a topic on which nobody works. Now, many of you are looking for research problems, right? You want to start working on Majorana zero modes, like calculate, I don't know, zero bias conductance peak at an end of a nanowire, knowing that there have been 1,000 previous people who have looked at this problem. No, you want to work on some problem where there's just a couple of guys doing it. Well, I can guarantee you up to today, my group is the only group working on edge vortices. And I welcome this competition. So join the club. I think they rule. They're absolutely cool. They're mobile counterpart to Majorana zero modes. Majorana zero modes are bound to an Abrikosov vortex, a fixed vortex. Edge vortices are bound to a biphase domain wall. They move along an edge mode. And so you can do all kinds of tricks, crossings, intersects, delays, play all kinds of fun stuff, which we're very familiar with in the quantum Hall effect. You can inject them on demand, deterministically, well resolved by a Josephson junction, which is an absolutely trivial piece of technology if you're in the field. So it's not difficult to inject them. The chiral motion, you know, almost automatically makes you braid them. They will braid by themselves. They braid by themselves. And you can detect them electrically. I mean, you could say, how do you detect the vortex? Well, you can detect them electrically as a sign. You can detect the braiding electrically as a sign change of the E/2 charge pulse. And this E/2 charge pulse is interesting by itself, I think. It's interesting by itself, in particular because it's a sharp observable. It's the mobile analog of the Su-Schrieffer-Hager, Yaakov-Rebbe bound E/2 charge, which we also know is a sharp observable. And here it's a sharp observable, which is mobile, which you can do the whole counting statistics. And in fact, if some of you are interested, I can even give you a pointer to an unsolved problem involving bosonization, the bosonization calculation of this. I'd be happy to discuss this with one of you if you're interested. Someone among you who hopefully knows what Klein factors are. And that's it. Friends, this is the end. And I probably am going to stop sharing, or I don't know what to do now.
No, I think it's okay. You just leave it there. I think at some point we'll have to shift back and forth. So this, I'll begin. Thank you. I think everybody can maybe raise their hands to clap if you like, or something in there. You see you get all kinds of raised hands now. Everybody's raising their hands. Very good. Thank you very much. Thank you very much. That's the way we clap in this webinar, I guess. Now lower them down in a minute because there is an anonymous attendee, but unfortunately I cannot call on you if you're anonymous. I don't think I have a way to tell who you are, but there's a question from this person. So I cannot give you the microphone being anonymous. This is asking how to be sure the 2π phase slip injects an edge vortex per edge and not two at the same edge. That's one question from an attendee that.
Yes, so basically, so a 2π phase shifts injects one pair of edge vortices, period. A 4-pi phase shifts will inject 2 pair of error vortices. Now, how much the phase will shift is completely under control. For example, if it's a voltage pulse, the integral of the voltage pulse will be a multiple. This doesn't have to be a quantized multiple. It could be roughly a multiple of EV over H, of 2 EV over H. So there's no there's no fine tuning. It doesn't have to be precisely 2 EV over H. But let's say if you're between 1 EV over H and 3 EV over H, you inject 1 pair. If you're between 3 EV over H and 5 EV over H, you inject 2 pairs. So that's how it works. So it's completely deterministic and on demand. And there may also be quantum fluctuations which produce edge vortices, but these are suppressed if the edge is much wider than the coherence length. These will be suppressed exponentially. So the only thing which will happen is this on-demand injection.
Okay, I think there's more questions from this anonymous attendee. Unfortunately, it doesn't work very well if you cannot converse. Yeah. So if you log in as anonymous, I cannot really tell who you are. So Nancy has a following up question what about, can you elaborate a little more on the comment about the Klein factors?
Yes, I could, of course, but I could. Why not? I mean, let me give you an open problem. It's a problem we've not been able to solve. And I don't have actually a student who says I'm going to solve it, so I don't think I'm giving away any secret. So here we calculate Coulomb generating function, and it's linear in psi, and so there's no noise. This holds for any lambda. This holds for any lambda. We have a completely different way of calculating stuff. In fact, these plots here, we calculate in a completely different way, a way which is not bosonization, a way which I trust much more because it's down to earth. And with this other way of calculating things, we find that sometimes there are actually higher cumulants. Not for this, not for the 2-pi pulse, but for other pulse shapes or other pulse increments, I should say, there are other terms here, plus stuff. And so bosonization fails. Now, the reason why I'm not publishing this as a failure of bosonization is simply because I'm insecure. And anyone who has worked on bosonization knows what will happen. A referee will write to you, have you worried about Klein factors? If you don't know what that means, you've not worked in the field. And Klein factors is this incredibly complicated, miserable stuff. And you can only publish in bosonization if you are deeply confident about what to do with the Klein factors. So I am not confident what to do with the Klein factors. I just ignored them. I get something which disagrees with just the conventional scattering matrix, the stuff which I know how to do. So I'm pretty sure I'm missing out on something. And if there's an expert, I'm willing to communicate with you, correspond with you. Leonid Levitov, are you listening?
Maybe
not. But, so you can write to me, and I'd be happy to communicate with you. And who knows, you might be able to solve this.
Okay.
By the way, I should acknowledge here the person who found this error in the bosonization is Fabian Hassler, who may or may not be listening in. He's the first author of the paper.
Fabian is probably there, or maybe not. Maybe on the
doesn't matter.
Channel.
He found this inconsistency in bosonization, and I don't know how to solve it.
So I think the next question that I'm going to call for. So Abhishek Banerjee, maybe you can ask your question. Can you unmute yourself? Yeah.
Hi. My question is about the gaplessness of chiral Majoranas, which you mentioned. And my concern is if these are really gapless modes, then does one worry about quasi-particle poisoning? And maybe that creates an issue with detection of these E/2 current pulses?
Yeah, so this is exactly the same problem anything has. If this thing, they're gapless, of course, but there's no sorts of quasi-particles, right? Because there's a superconductor which doesn't have unpaired fermions. If the superconductor has unpaired fermions, you're dead anyway. And there's an insulator here. So even though the mode is gapless, there's no source of quasi-particles. Now here, of course, is a metal contact. And so if you have metals nearby, so this is exactly the same story for any superconducting implementation. If there are sources of quasi-particles nearby, you have to remove them. And
but the gaplessness is not a problem.
No, the gaplessness themselves is not a problem. It's just, but because there's a superconductor, and the superconductor bring in quasi-particles. So no, I don't think that should not be an issue.
Sure,
so
I should have perhaps, I should have perhaps emphasized more that if you're going to use this for qubits, the qubit degree of freedom will not be the E/2 charge. This is not a charge qubit. The E/2 charge is very convenient to detect it, but the qubit degree of freedom will be fermion parity. I didn't mention this word at all because that goes on a tangent. But if you're in the field, you know what I mean. The qubit degree of freedom is the fermion parity, and the charge degree of freedom is just an easy way to measure it, but the charge is not topologically protected. It's the qubit degree of freedom which is topologically protected.
I'm going to ask, because there's a few raised hands in here, but it may be from the clapping part. So the ones that do have questions, I'll remain the raised hands. It's okay, I will call on you. There's very interesting questions from this anonymous attendee. I'm going to try to see if answering live means that I allow them to talk. Would you like to answer your question live? No, I guess not. I don't know how it sadly works. So let me just read, because unfortunately I cannot allow the speaker for this person if it comes anonymous. So now I learned this thing. Let me ask a few questions that he mentions and follows up on. So I'm just going to read them out loud to you, Carlo. Okay. So I think while you were discussing these things, this first response to this talk was this question regarding whether they come in one or two at a time. There was this question following up about what about MZMs in Majorana zero modes, I assume, in nanowire superconductors links that are currently being investigated in great detail. Can they be braided? And I assume it's the same person. How does this work if keep the middle grounded and apply voltage bias to the leads? This is naively, this should be just a gauge transformation. This is related to what you were experiment that you were having. And you can pick the last question from him, for him or her. What is the advantage of doing bosonization compared to working with a fermion world?
Okay, let me go from last to first.
Very good.
So bosonization this was discovered by Levitov, Lee, and Lizovic. Bosonization allows you to derive results. Once you've learned this method, it allows you to derive results in 2 lines, which otherwise would take at least 2 or 3 pages. But it's an advanced technique, and so you may feel uncomfortable with it, and you may be worried that you're overlooking something, whereas the conventional way is just, elementary Schrödinger equation. So, it's something we're much more familiar with. So that's just to mention one crazy, I mean, if you've never seen it, it looks like a crazy equation. So this commutator here is, of course, the thing which makes everything happen here. And that this is a density, but the density looks kind of okay. That's a bosonic density, but there's this anomalous Kac-Moody commutator here, which makes everything happen. And the first time you see it, you think this is really strange, so you have to get used to it. So it's just a very convenient way to derive stuff in 1 page. In fact, I can already say here in 2 slides, I derived things which in the paper which we put on the archive took us 15 pages or 10 pages. So that's bosonization. There's no other advantage, and if you don't.
Okay.
There was the first question, Majorana zero modes bound to nanowires. So that's the alternative approach. So these zero modes are always bound to vortices. It's always like that. They're always bound to vortices or to defects. There should be more precise defects. So the end point of a nanowire is perhaps not quite a vortex, it's a defect. But it's an immobile defect, right? So there have been proposals in the literature to take this wire and somehow move it around in real space, but that's not going to happen. So if you want to braid vortices bound to endpoints of wires, you have to use a different way. You cannot just move them. There's a method which is called braiding by measurements. Actually, the best I could do is I put a paper, Lexou's lecture notes on the archive just recently. So if you just Google me and look at these Lexou's lecture notes, there it explains how to braid zero modes bound to immobile stuff. You cannot use this method. It's a totally different world, and it has its advantages and disadvantages.
Okay.
And then there was this. Yes.
There was this other question.
Yeah, this other question, which
I think it was more related to the initial. He was asking this question while you were answering another question. This one,
yeah.
I think.
I don't know.
How does this work if you keep the middle grounded and apply voltage bias at the leads naively? This
I don't. I mean, okay, okay. There's one other contribution which I should acknowledge, who may even be listening into Michal Moskalets. I'm not sure whether you're here.
The anonymous attendee.
Yes, anonymous attendee. So you could ask, why not do this stuff in the normal? Just give me a tunnel junction. Give me a tunnel junction. I apply a phase pulse over the tunnel junction of 2 EV over H, and I have my fractional charge. And the answer is yes. And this is what Michal Moskalets studied. You can do it. You would have to absolutely fine tune this. I mean, there's nothing, if you're in a normal metal, there's nothing magic with the phase pulse of 2E over H. So you would have to fine tune it, but you can inject the same fractional charge in a normal metal if you fine tune. The advantage for doing the voltage pulse across the superconductor is no fine tuning required. And so applying a constant DC voltage will not give you this set of pulses which I show here. This set of pulses which I show here is the result of a DC voltage here, right? This is the crazy thing. This is not a voltage pulse. I have a DC voltage, which creates well-defined voltage pulses. If you would apply a DC voltage here, you would not create well-defined voltage pulses.
Let me give the floor to Igor Mazen, that has his hand raised. I assume that's a question that you have, Igor? Maybe not. Is there a question from Igor? Yeah.
No, that was, I raised hand when you encouraged us to raise hand to upload.
Oh, to upload, okay. Because I also told him to lower it, and that way I can tell.
Oh, then I guess I didn't realize that I can also lower.
So there's two more with the raised hands. I'm none. If you actually are, okay. So let me ask you. Actually, Anton, hang on. Let me get Anton here. So Anton is going to be speaking now. So let me go ahead.
I'm not sure that experts and co-authors.
So this is so Anton. He's definitely. I'm not sure if you're allowed.
No, I can also ask a question anonymously.
Oh, that was you with anonymous.
Yeah, so I was wondering. I think. Do you have any idea how to make these this problem interacting? Because so far this is still a non-interacting Hamiltonian. We are still looking at a time-dependent problem of classical of non-interacting fermions, which is essentially something that the classical computer can do very efficiently. So do you know a way to work around this?
Oh my goodness, I'm not sure what you're referring to, but are you referring to the fact that Majorana zero modes can only give you Clifford gates, and so they cannot give you universal quantum computation? I haven't solved that problem for us. There's no solution to that. So we all know that Majorana fermions can only create.
No, but so you don't have Majorana fermions because
I have Majorana zero modes here.
They give you Clifford gates only if you also have a joint parity measurement, but you don't. You can only braid, but you cannot measure parity of 4 Majoranas, which is what you would need to have in addition. So
yes, that is correct. At least at this moment, I would not know how to do 4 Majorana measurements. That's correct, Anton. I would not know how to do that.
Maybe, and parity detection, something like this?
No, I mean, you're correct. I do not know at this moment how to do 4 Majorana parity measurements. Sure. I'm not saying it cannot be done. Yeah. I would have to think about it, but I would not know how to do it.
All right.
Very good. Let's see. Is there any? Let me see if I can find any other hands. That is, I'm none. I think we're not allowed today to ask you a question. You have a question? I'm none. You've been given the floor. I'm not sure if it was because this must have been that they just wanted to clap and sure. Okay. I have a bit of a follow-up question on myself. Coming from the spintronics world and all things with domain walls and pi domain walls that we have also in antiferromagnets, which have a lot of analogies to superconducting states. Here, once you get into the superconductors and the vertices themselves, they're still classical objects. Is there something like that on braiding that you can show classically? Or where does the quantum come in?
No, this is of course the magic of this, right? Braiding is classical.
That's what I was saying.
Braiding is classical.
But can you do a braiding an antiferromagnet, for example?
Braiding is classical. There's no tunneling, no quantum interference. It's a completely classical thing. Of course, you would need to create the notion of a pi phase domain vol, of course, or the notion of a Majorana zero mode itself. I wouldn't quite know how to, this robust individual entity. I wouldn't know how to describe this without quantum mechanics. But the braiding operation itself is just a classical thing. There's no tunneling involved, no interference involved, which is true.
Okay, good to know. This is what I was suspecting, but I wanted confirmation just in case I missed something.
No tunneling, no quantum interference, purely classical, just move one stuff around the other.
So I have a question from Brett. I think we would like to ask the following question.
Yeah, thanks for taking me on. This is just a very simple question. I'm a graduate student, University of Minnesota, experimentalist. When you talk about injecting these vortices into the edge mode, will you talk about the physical nature of this? Because when I think of a vortex, I think of 2 dimensions, and then these edge modes are obviously 1-dimensional. At least.
Yeah, that's true. But you can also think of vortex as something. My way of thinking of vortex is a branch cut. You have a phase which evolves by 2 pi, and you know that if you have a phase which evolves by 2 pi, you need what's called a branch cut. Logarithm. So you need to cut your thing. And so in this case, the edge or a line perpendicular to the edge is the branch cut. So my way of thinking about vortices is just the way you're probably familiar with the notion of, say, a branch cut for a logarithm, right?
Sure.
The negative real axis. And so the point where the branch cut ends is the vortex. That's the core of the vortex. And in this way, it's the same thing. So it's just a line which you draw somewhere on the plane. And if you cross the line, phase jumps by 2 pi. And whether this line is bound to an edge or just somewhere in the middle of the sample doesn't really matter.
Got it. Okay, so the coherence length just doesn't matter in this situation.
Well, the coherence length says whether the phase will jump really abruptly as a step function or whether it will be smooth. So if you go more inside, the same thing with the vortex. The vortex could you thought of as a point, but you could also think, no, it's not a point. It has actually a spatial structure. And the same thing here. This phase will not jump abruptly, but if you have a finite coherence length, the phase will jump smoothly.
All right. Thank you very much.
I think maybe Gisela Schutz has a question.
Do you hear me?
Yes, we can hear you.
So thanks for this really impressive talk. I think for a 5 years project, you must have some thought of the real experimental realization to test your theoretical approach.
Oh, absolutely.
Do you know what the experimental drawbacks or difficulties or let's say positive challenges will be? Yeah.
So I would say the primary thing is, please give me Majorana edge modes. Right? And no, I mean, this is they're experimentalists for whom this is their career. Their career is, we hoped that, like 20 years ago, we hoped that strontium ruthenate would do this. And there have been research groups who have their entire career trying to demonstrate Majorana edge modes in strontium ruthenate. It never worked out. Then now we have a whole host of new materials. We have many more ideas how to do it. I'm kind of optimistic that in the next couple of years, we'll have a robust platform of Majorana edge modes. But this is not something to which I can contribute, right? It's a material science problem issue. I can just applaud the experimentalists who are not giving up and are trying to create the Majorana edge modes. Once you have Majorana edge modes, there's no shortage of experiments you can do. This will be one of them, but there's a whole host of things. You can really spend just as you can spend an entire career exploring the quantum Hall effect in gallium arsenide, you can spend an entire career exploring Majorana edge modes in superconductors once you have them. We thought we had them with this 2018 experiment. It turns out to be wrong. And
let's see.
It can be live. That's how physics works.
Absolutely.
It's important to risk in physics. If you're not willing to be wrong, you're not doing interesting enough things. I can tell you that. as a philosophy that I think we should all bound for. Let's see. Okay, Dimitri. Let me actually hang on a second. Give the floor to Dimitri real quick. I hope I'm doing justice. So, Dimitri, I believe you can talk now if you like. You have to unmute.
Hello. So I wrote my question, but am I right? Do you hear me?
Yeah.
Hello. Am I right that the fusion of two H vortices corresponds to a change of fermion parity in the superconductor?
No. The fusion is just the detection process. The change of parity is the braiding of the vortices. When one vortex overtakes the other vortex, they exchange a fermion. A fermion hops from one vortex to the other, flipping the sign of the charge. The fusion is just the process by which you measure this. So the braiding is the change in fermion, the switch in fermion parity.
Okay, thank you.
All right, so I don't see any more questions at the moment. So just the same as we clapped before, maybe you can all raise our hands to clap once again to Carlo. And I would like to really thank you once again for being the second speaker of this series, and all the 400 attendees that attended between here and YouTube, for having taken the time. And once again, so I hope you guys are enjoying this, and encourage people to attend and to sign up to our mailing list, that we will continue in this spirit. So with that, I wish you all a very good time. And maybe, Carlo, if you want to say the last words.
No, thank you. It was an enjoyable experience.
Wonderful. Thank you all. And I hope to see you next week on the next session.